Hi guys, sound check.
Seems like it works.
Okay, the time has come. I think we should start. Okay, well, the time is passing. We're becoming more mature, and we're no longer satisfied by just simple groups. We need something more interesting. Today, I'm going to be talking about rings. So yes, we're becoming the lords of the rings, and you will see in a minute what this means. Okay, so let me start with the, okay, so we're going to deal with rings. I want to start with the definition. So as usual, when we define an abstract algebraic stuff, we first define the data we need to define the object, and then we pose the axioms. So the first part is the data. So we're the data. But first of all, we want to fix a set. Second, we need a binary operation. And third, we need another binary operation. So like we need more operations. So the first one will be called addition, and the second one will be called multiplication. So this is just addition. This is just the name of the operation, and this is multiplication. So this is our data. So again, a set and a pair of operations. And now we want to pose the axioms. So the axiom number one, we want the addition to be good. This simply means that if we consider just the set R with the operation plus, this must be an abelian group. Or just a commutative group. So the operation plus must be associative. So there must be a neutral element, which is denoted by 0. Each element must have its inverse, and the other of the operands doesn't matter. Next, we want multiplication to be left and right distributive over addition. So multiplication must be distributive over addition, which means that we must have A times B plus C equals A times B plus A times C, and also A plus B times C, so there are two properties, equals A times C plus B times C. For all possible elements A, B, and C from the set R. So for all A, B, and C from the set R. This means that the multiplication is distributive over addition. So the usual properties we have for like integer numbers, real numbers, and so on. Also, we want the multiplication to be not very bad, at least. So what does it mean? It means that, first of all, multiplication must be associative, is associative. Well, explicitly, this means that we don't care about the brackets. So again, for all possible elements from our set R. And at the end, we want the last axiom, the fourth axiom, says that the multiplication must have a neutral element. So there exists neutral element for multiplication. So there exists element 1 such that 1 times A equals A times 1 equals A for any element A R. So if we have all these things subject to these rules, then R with addition, with this pair of operations, addition and multiplication, is called a ring. So here, by definition, so in this case, this set with these two operations is called a ring. This is not the most general definition of a ring, but this is one of the more useful ones. So this is one of the convenience way to define a ring. Also, if we have, let me use a different color. If additionally we say that multiplication is commutative, so if multiplication is commutative, which is A times B equals B times A for any A and B on the set R, then the ring R is said to be commutative. So R plus multiplication is the commutative ring. So just remember, the addition is always good. So R with addition is an abelian group. So the operation is best possible. The multiplication need not be very good. So if we pose some additional property for multiplication, so this property appears here near the name of the ring. So if multiplication is commutative, then a ring is commutative.
Sorry, can I ask a question?
Yep.
Isn't commutative ring a kind of field will be?
No. For example, the ring of integer numbers. So the set of integer numbers with usual addition and multiplication, they are not a field, but because not every element is invertible. Like
Yes, I understand.
So yeah, but this is what I'm going to define now. I want to give you the definition of a field, and you will see what's the difference between these two notions.
We actually had definition of a field on our linear algebra course. Yes, we had it.
But just in case, I want to complete the definition and pose all the conditions for the field. So if additionally we have other two properties. The first one, every non-zero element. Here, 0 is the name for the neutral element with respect to addition. So if every non-zero element is invertible, invertible here with respect to multiplication. So let me formulate it precisely. So if for every non-zero element there exists an element b such that a times b equals b times a equals 1, and also if the neutral element with respect to multiplication is different from the neutral element with respect to addition, which means 1 is not equal to 0. In this case, r plus and multiplication is called a field. So let me show you the whole list. So when we go from 1 to 4, this simply means R is a ring. When we go from 1 to 5, it means that R is a commutative ring. And when we go from 1 to 7, this means that R is a field. So in case of the field, every non-zero element must be invertible, and 1 is not equal to 0.
Excuse me, can I ask you a question, please? Like,
yep.
We define the ring R plus as an abelian group, so we don't have to say that there is also a neutral element for it, because like I see that we only define the neutral element for multiplication. So we say that like since R plus is an abelian group, we don't have to define that there exists a neutral element for the additive notation. I mean, like for plus.
Well, but it's included in the first example.
So we don't have to write it if we write that it's an abelian group, yeah? Yeah,
so I mean, it just simply wrapped into the first statement. Like if you want to give a more detailed definition, so what does it mean that this thing is an abelian group? It means that you have 4 conditions. So there are just 4 conditions hidden here in the first line. So if you wish, I can write them explicitly, but this is just a simpler way to give the definition. So you don't go through all the possible details. You just say that R plus is an abelian group.
Okay, thank you.
I'm not 100% sure that I understand the question, but if it's still unclear, just reformulate the question.
No, okay. Mm-hmm.
Okay. So okay. So usually this when people give this definition, they say that R is an associative ring with an identity. So if you read something, you may see this longer definition, but I don't care. The word ring will always mean well, what's written here. So that's just for simplicity. I just don't want to pronounce all these long words. And actually, it helps to avoid confusions if you use shorter terms. Okay, now I want to give you several examples. As usual, when we see an abstract definition, it's very helpful to see at least a couple of examples. So examples. Example number 1. Let's take a 1-point set. Let me denote it like this. So R is just a set consisting of just one element, and I'm going to denote this element by the star. Now, if you have this set consisting of one element, you have only one possible binary operation. So you have only one binary operation, which takes this pair to this element. And this will be our addition. And since this is the only operation, the multiplication is also given by this rule. So we have no options since that's the only operation. Well, what I'm saying that this triple defines a ring. And actually, this is a commutative ring. In this case, the element star is the same element as the neutral element with respect to addition. You see, when you add this guy to this guy, the result is exactly the same. So this is a neutral element with respect to addition, and also it's a neutral element with respect to multiplication. So this is at the same time the element 1. So this is an example of a trivial ring. The ring consisting of one element. In this case, this element is also the 0 element and also the identity element. So that's one example of a weird ring consisting of just one element. Okay, so now let me give you another example. So consider the set of integer numbers with usual addition and multiplication. So this is a commutative ring. So I believe no one needs to prove this because we use this ring like almost all our almost whole life. Now, another example. Let's take the real numbers with addition and multiplication. Then the real numbers form a field. This is a field. Another interesting example is a ring of matrices. So, example number 4, we may take
maybe ring of square matrices, because
yeah, square matrices. Yeah, we should take square matrices of the size n with usual addition and multiplication, and this is a ring. This is not a commutative ring, but this is just a ring. And one another example, if suppose that A is a commutative ring. Oh, by the way, I just forgot this example. The reminders modular natural number n also form a commutative ring. And the last example, if you take an arbitrary commutative ring, A is a commutative ring, and you may define a polynomial ring with coefficients in A. It's denoted by A of x, and it consists of all polynomials. So it consists of all pictures of this form, where n is any natural number, and all the coefficients are in the ring A. So we just consider the set of all pictures having this form. Well, these, if we have two pictures, then they are the same if and only if the corresponding coefficients are the same. So these are not functions, these are just pictures. But we can add and multiply them by the usual rules, as we do.
Can I ask?
Yep.
I also want to know, is there some way to identify a polynomial, like just seeing a function and identifying that it is a polynomial, especially in the most general case, like commutative rings?
Could you repeat your question?
Is there some way to identify the polynomial just by considering the behavior of it as a function, not by its form?
No. In general, if the ring A is small, there is a difference between functions and polynomials. So different polynomials may give exactly the same functions. I'll give you an example in a second. But just in case, let me give the definition of the operations. So if you have two polynomials like this one, let's say k, and another polynomial So the addition is given by the usual formula, like this. And multiplication is given like this. Okay, here. I don't want to write the indices. It's just simpler to write it without indices. So here, d, x to the d, and here sum of am times a, let's say au times bv, where u plus v equals d. So I mean, the summation goes through the element appearing here. So k from 1 to something, k from 1 to something, and here k also goes from 1 to something finite. So these are the formal rules to define the multiplication and addition between two different polynomials, and this becomes a commutative ring. And so f(x) is a commutative ring. Now, there was a question how to compare the polynomials and the functions. So what does it mean exactly? So if we have a polynomial like this, then it defines a function. So from where to where? It defines a function, let me denote by f with a hat, from a to a, which takes an arbitrary element, say a small, to the element of this form. We just substitute element a instead of the variable x. So so this allows us to define a function, but it may happen that different polynomials, so different pictures, give exactly the same functions here. And here is an example. If you take, for example, z2 to be a, and you consider the polynomials over z2, so let's take the function fk to be x to the k, so just kth power of the variable x. So all these polynomials are different, but if we consider the corresponding functions, how do they work? So they take 0 to kth power of 0, which is 0, and they take 1 to the kth power of 1, which is also 1. So all the functions are the same for any k and k prime. So that's why there is a difference between polynomials and the functions. So we want to somehow to distinguish polynomials by their coefficients and not by their values at some points. Well, it will be more convenient, and you will see, like probably in the next lecture, why it's more convenient and why we need this. But did I answer your question?
Yep, sure. That wasn't exactly that wasn't exactly what I meant, but yeah, you know. Yep.
But okay, so if you still have a question, so could you ask it?
No, basically, I understand that my very first question was kind of pointless, so I guess that's quite enough.
Okay, thank you. So so let me proceed. So now so if we have a ring, we may have something, well, like when we have vector spaces, we have subspaces. So now I want to discuss the notion of a subring. So definition. So let's suppose we are given a ring. This is our context. So this is a ring. And I want to define a subring. So this is what I'm going to define. So what is this? So first of all, the data. T must be a subset. And now the axioms. First of all, T with respect to addition must be a subgroup in R with addition, is a subgroup. Second, T is closed under multiplication. Is closed under multiplication, which means that if we have two elements inside T, then their product must be also inside T. And the third property, the identity of the ring R must be inside T. So in this case, we say that the subset T is a subring in R. Well, for example, Z is a subring of the ring of the field of rational numbers, or Q in R is also a subring. Or another case, the diagonal matrices. So if you take D to be the set of diagonal matrices, it's a subring in the ring of all square matrices. These are the examples of a subring. Well, okay, so we want to study rings. How do we do that? Well, there are several ways. The way number one is the element-wise approach. So we want to study different types of the elements we have in our ring. And I want to give you a brief description of types of elements we are interested in. So there are 4 different types of elements. So suppose that, elements of rings. So what kind of elements do we have? First of all, well, suppose that R is a ring. So let's fix a ring. Now, let X be an element. We say that it's invertible. Well, if there exists Y such that XY times YX equals 1. Here, 1 is the neutral element with respect to multiplication. So this is just the usual definition of the invertible element with respect to some binary operation. And in this case, we will denote the element Y by the X to the power of -1. So actually, X to the power of -1 is the element Y in our case. So we know that the inverse is unique if it exists. So in this case, we will denote it just by X to the power of -1. Okay. The next thing, we say that an element X is a left zero divisor. Left zero divisor. If there exists an element Y in R, Y is not equal to 0, such that X times Y is equal to 0. So just in case, left means that X is on the left. So if we can take an element X and after multiplication by a non-zero element on the right, the result is 0, then X is called left zero divisor. So there is a similar definition of the right zero divisor, which means that Y times X equals 0. Oh, and just by the way, I forgot to define the notation. The set of all invertible elements will be denoted by R star. So this is the set of all invertible elements. In this case, I will denote the set of left zero divisors by dl of R. This will be the set of all left zero divisors. dr of R is the set of all right zero divisors, and all of them are just simply the set of all zero divisors. So zero divisors in the ring is just the set of all left and right zero divisors. In case of the commutative ring, there is no difference between zero and between left and right zero divisors, but in general there is a difference. But we will mostly deal with commutative rings, so it will be not that important.
I have a question.
Yep.
In this case, we consider just usual multiplication.
What does it mean, usual multiplication? R is a ring, which means that it has two binary operations. One of them is denoted by plus, another is denoted by dot. And here I use this second operation of the ring.
But I thought that our zero is a neutral element for plus, not for multiplication.
Yep, it's a neutral element for the addition. Yes. But so this is an equality. So I mean, we have this set R, and X and Y are some elements of this set R. When I apply this binary operation, which is multiplication, I will get an element of the same set R. 0 is also some fixed element of the set R, and it makes sense to ask, are they the same or not? So if I can find an element Y such, well, will all those properties such that the result of this multiplication is equal to 0, where 0 is that particular element, which is the neutral element for the addition, well, then X is called left zero divisor.
Oh, okay, I got it. Thank you.
GL and DR are divisors of zero.
GL are the left zero divisors.
These sets are divisors of zero. Yeah?
Yeah, and these are, just zero divisors.
Okay.
I mean, they took, so left or right zero divisors, they're just called simply zero divisors. So if I don't want to specify the side, I just say zero divisors, and this means either left or right zero divisor. Are there any other questions? Okay, so let's move next. So let's move to the next thing. Here I want to define an nilpotent element. So an element X from the ring R is called nilpotent or nilpotent element if there is a natural number n such that x to the n equals 0. In this case, X is called nilpotent. And the set of all nilpotent elements will be denoted by this. Nil R is the set of all nilpotent elements. Okay. So, I mean, if X was 0, like if we take X to be 0, then X to the power of 1 is equal to 0, so it's also nilpotent. But it may happen that the initial element X is not necessarily 0, but after raising it to a power, the result becomes 0, like we know with some matrices. It may happen that a matrix is not 0, but after rising it to a power, it becomes 0. So it may happen. And the fourth definition we say that X from the ring R is idempotent, if X squared equals X. And the set of all idempotents will be denoted by ER. Okay. Well, it must be unclear why do we care about these particular properties of the elements. You will see later that they just help us to distinguish different rings, to understand their structure, and so on and so on. So the role of these elements is probably completely not clear now, but it will be more and more clear when we will deal with some specific rings, and we will describe several examples. But just in case, let me just repeat what happens here, just to summarize. Like, we have 4 different notions for the elements. So the first thing is invertibility. An element is invertible or not invertible. Then zero divisor. An element is either a zero divisor or not. And in non-commutative ring, we have 2 options: left zero divisor or right zero divisor. Then we have a notion of a nilpotent element, and then notion of an idempotent element. So the idempotent means that if you raise it to a power, nothing's changed. Okay. Just in case, let me give you several examples. So, examples. If we take the ring Z with the usual addition and the usual multiplication, then the set of invertible integers is just the set of plus minus 1. The only zero divisor here is the element 0. The only nilpotent element here is also 0. And the only idempotent elements here are just 0 and 1. So this is the full description of the special elements in the ring of integer numbers. Oh, and by the way, let me show you a picture. I just completely forgot about the picture. So suppose that we have a ring R. So then this is the set of all invertible elements. And here is the set of all zero divisors. So they do not intersect. Invertible elements and zero divisors, they do not intersect, and there may be something between them. The elements which are not invertible, but they are not zero divisors. This is what happens in case of integer numbers. Like the element 2 is not invertible as an integer, but it's not a zero divisor. Also, if we have nilpotent elements, they live here. The nilpotent elements live here. Yeah, this is how these elements lay inside an arbitrary ring. Yeah, and if we have, well, I don't want to write idempotents here. So,
and why
yeah.
Why is 2 not invertible?
Why is 2 is not invertible in the ring of integers?
Yeah.
Because there is no other integer such that you multiply 2 by another integer and the result will be 1.
Ah, it's 1/2.
There is a rational number. So
okay,
2 is invertible in Q, but it's not invertible in Z.
Okay, thanks.
So it's important to specify the ring you're dealing with. So yeah, but that's the right question, because it may be invertible, or it may be not, and it depends on the ring you chose. So if the ring is Z, it's not invertible. So well, okay. I don't want to specify all other examples. I just want to briefly mention something like if you take R to be the ring of square matrices, then what are the invertible matrices? Invertible matrices consist of all non-degenerate matrices. And the zero divisors are all the other matrices. So they're just matrices with determinant being equal 0. I don't want to describe idempotence or nilpotence in this ring, but it should be clear that GLN is precisely the set of invertible matrices, and the zero divisors are all degenerate matrices. Okay, now I want to switch to a different subject. So we discussed some specific types of elements, but modern algebra doesn't like to deal with object like element-wise. We want to have some tools, like more abstract tools, which are usually more powerful, or they allow us to do like some tedious work in a simple manner. So here we have the notion of ideal. So what is an ideal? So suppose we're given a ring, and I want to define an ideal of this ring. So as usual, let's start with the data. The ideal must be a subset. First of all, this is a subset. And now the axioms. Axiom number 1, if we consider this subset with addition, it must be a subgroup in R with addition. So this reminds the definition of a subring, but the difference is the second property. For every element X from the ideal, and for every element R of the ring, we have X times R belongs the ideal, and R times X belongs the ideal. So let me repeat the definition. So an ideal is a subset of our ring such that it closed under addition. Well, actually, it contains the zero element, is closed under subtraction. So with each element A minus A is also in the ideal. And also, we may multiply any element of the ideal by any element of the ring, and the result will be inside the ideal. So here it's much stronger than being closed under multiplication. So if we take any elements of I, the product must be inside I. But we need more. Again, please.
Do we consider like left and right ideals?
Well, I don't want to specify left and right ideals. There is a notion of a left ideal and there is a notion of a right ideal. In commutative case, it doesn't matter, but I just don't want to go into those details. Because usually left and right ideals in non-commutative case are interesting when we want to deal with modules over rings. But it's not going to happen. We're talking about modules over rings. We don't have time for that. We have more interesting things to do. I want to stick to some interesting problems, to some applications to computer science. So I just don't want to go to abstract algebra. But you are right, there are such notions.
Yes, okay.
Okay, so let me give you examples, some examples. So, examples. Let's take Z with usual addition and multiplication. So consider the subset given by n times Z, where n is an arbitrary integer numbers, and n times z simply means n times m for any integer m. Then this set is closed under addition. We know it's a subgroup in Z with respect to addition. We already know that all possible subgroups with respect to addition are of this form. And now it's clear that this set is closed under multiplication by any integer number. So if we take an element x here, and we take an arbitrary y from Z, then x times y is inside n times z. So this is the property of being ideal. Like we take an element from the ideal and any element from the, and the result is again inside the ideal. Okay. Now, let's describe, well, actually, all possible ideals here are of this form. So let's prove this. So the claim. So I want to describe ideals in several rings. The first thing, let's take the ring of integer numbers. Then, and suppose that I is an ideal. Well, this triangle means that I is an ideal. This is how you denote that some subset is an ideal in a ring. Then I is of this form. So every ideal is of this form. Okay, let's prove. Well, so, let's take an arbitrary ideal. Well, since it's a subgroup in Z with addition, it must contain the zero element. So there must be zero inside I. And now we have two options. Either there is no other elements except zero, or there is something which is not zero. Oops, inside I. There is something inside I which is not zero. There is an integer which is not zero and it belongs to I. Well, in the first case, I is equal to 0 times Z, so it has the required form. So now we want to consider the second option. Well, here we have two options again. Either x is smaller than 0 or it's greater than 0. Well, in case x is smaller than 0, we have minus x inside I because I is a subgroup, and minus x is greater than 0. So in both cases, we may assume that we have an element x greater than 0, which is inside our ideal I. So now we want to define n to be the least positive integer inside I. So this is the least positive integer inside I. So let me show that in this case, I is equal to nz. So we need to show that I is equal to nz. But just in case, are there any questions until now? Okay. So what do we know? Since n inside I, just by definition, then n times m for any m in Z, n times m must be inside I by the definition of the ideal. because, yeah, just by definition. So this proves that this inclusion, that the right-hand side NZ belongs to the left-hand side I. Now we want to prove the other inclusion. Let's take an arbitrary element x from I, and let's divide it by n with remainder. So we have x equals q times n plus r, where r is not greater than n and is positive, non-negative. But let's represent r as follows: x minus q times n. But here, x by definition was from the ideal I. That was our choice. N was also from the ideal I. We have chosen n to be the least positive element inside I. By definition of the ideal, q times n is also inside the ideal I. And since the I is an abelian subgroup, x minus this product is also inside the ideal I. So the result here must be inside I. But now, you see, R must be something between 0 and n. But it could be 0, but it cannot be n. And n was the least positive integer inside the ideal I. So if R is not 0, then it's a smaller integer inside the ideal I, which is positive. And this is a contradiction. So R must be 0. So by the choice of n, R is 0 here. And this simply means that x is equal to q times n, which means that x belongs to n times z. And it proves the other inclusion. So, are there any questions? Okay, I hope it should be clear. Well, let me see. Okay, what I want to show next is I want to describe. By the way, was it too slow? Should I prove these things faster, or is it okay?
It's okay, the pace is well enough.
Okay, so now let's consider another ring, Zn, with addition and multiplication, where n is just an arbitrary positive integer. So the claim is that every ideal, so if I is an ideal, then I is equal to k times Zn, where k divides n. So every ideal has this form, k times Zn, and k must be a divisor of n. So first of all, if we take an arbitrary k and multiply and consider this set, which is k times m, where m is an arbitrary remainder, then this is an ideal. This is just a remark showing that every subset of this form is an ideal. So we just need to show that if we're given an arbitrary ideal, it has this form. And here we don't even need this additional assumption that k divides n. But since it's ideal, and if k here doesn't divide n, we can choose a different k, say k prime, so that k prime times Zn defines exactly the same subset, and k prime divides n. Okay, so now suppose that I is an ideal. Again, it must contain the 0 element, and we also have two options. Either there is only a 0 element, or we have something x, or some x which is not 0 inside I. So in this first case, it means that I is equal to n times Zn, and we have k to be equal n. So now we want to consider the other case. And again, in this case, so x is an element from Zn, so it's a reminder, so it's an element from 0 to n minus 1, at least it's non-negative, and well, it's actually positive since it's not 0, and we consider k, we define k to be the least non-zero element of the ideal I, the least x in I, such that x is not equal to 0. And now we want to show several things. The thing number one is that I is equal to k times Zn, and the second thing that k divides n. These are two things we want to show here. So this is what we need. So the first item is shown exactly the same as we did in the previous claim. So I'll try to be quick. So the claim number one. So again, this inclusion is clear by the definition of the ideal, since k is inside I, then multiplying by anything of the ring Zn, we will get the result inside I. So this is okay. So for the other inclusion, we take an arbitrary element x from I, we divide it by k with the remainder r, and the remainder r must be x minus qk. So this is inside ideal I. This is also inside the ideal I. So k might be inside I, but since k is between 0 and k minus 1, and k was the least possible non-zero element of the ideal I, by the choice of the element k, we have here that r must be 0. So this is exactly the same as we did it before. So now we want to show that k divides n. So here's the trick. Let's take n and divide it by k with the remainder. And now consider, and as as usual, we have this inequality. R is between 0 and k minus 1. And now let's consider this equality modular n. In this case, it means that 0 equals k times q times k plus r in Zn. This is equality in the ring of reminders. But this simply means that r is equal minus qk in Zn. But since k belongs to the ideal, then minus qk also belongs to the ideal. So r is an element of the ideal. But this element is strictly smaller than k. So by the choice of k, again, we get that r must be 0. And this simply means that n is divisible by k. Okay. Let me see. I want to. Okay, I'll skip one claim. Yeah.
One line above. Why if x and x belongs to I and qk belongs to I? That's one line above. Yeah.
Again,
why does it imply that r is equal to 0?
Oh, why it's implied that r is equal to 0? So let me show you. So by definition of k, the k was chosen to be the least non-zero element of the ideal I.
Oh.
And now we have r to be an element of the ideal I, and it's strictly smaller than k.
Okay, I see.
So since k was the smallest non-zero, r must be 0. So let me denoted like that. So that's the reason. So this is the usual way to prove something about integers or reminders. You just take the smallest possible something, you divide by it with the reminder, and you will get that the reminder is 0. So this is the usual way to handle such kind of problems. Okay, so now I want to give another definition. So in case of abelian groups, we have a way to compare different groups. And to compare different groups, we use homomorphisms. And in order to say that two different groups are the same, we use the notion of isomorphism. So here we also have a homomorphism for rings and an isomorphism for rings. So let me formulate precisely what does it mean that we have a homomorphism or an isomorphism in case of rings. So homomorphisms and isomorphisms. So suppose we're given two rings, R with addition and multiplication, and S with its own addition and multiplication. And I want to define a homomorphism, phi from R to S. So again, phi must be a map from the set R to the set S. So this is a map. So it takes elements from R to the elements of S. And now the axioms. Well, the first axiom, it must preserve the addition in the sense phi of A plus B equals phi of A plus phi of B for any A and B of R. The second property, phi must preserve the multiplication. So phi of A times B equals phi of A times phi of B for any elements A and B of R. And the third property, phi must preserve the identity element. So the identity of the ring R must go to the identity element of the ring S. So, and as we know, if, well, since R with addition is an abelian group and S with addition is an abelian group, the property number one means that phi is a homomorphism of the abelian groups. Like if we forget the multiplication on R and S, then the first property means that the map phi is a homomorphism of abelian groups. But if we have a homomorphism of groups, we know that the neutral element goes to the neutral element and the inverse element with respect to the addition goes to the inverse element with respect to the addition. So in this case, it simply means that the zero element goes to the zero element. So we don't need to pose this property here. So this is the notion of a homomorphism. And if additionally we have, so in this case, so let me say phi is a homomorphism, and if additionally we have that phi is a bijection, then phi is an isomorphism. Well, it's called an isomorphism in this case. And as before, as I mentioned, then how do you think of an isomorphism? So it's a bijection, which means that you rename the elements of one ring by the names of the elements of the other ring, and you rename one operation by the other, one multiplication by the other, and the identity becomes the other identity. So in this case, well, if we have an isomorphism between two rings R and S, well, they're simply the same. So the like technically, this is exactly the same ring. They're just given by different sets with different names for the elements, with different names for the operations, but essentially they are the same. And if there is an isomorphism between two rings, so if we have an isomorphism, phi from R to S is an isomorphism, we will say that R and S are isomorphic. So exactly the same as it happens in case of abelian groups. So a homomorphism is a map preserving operations, and an isomorphism is a bijection preserving all the operations. So let me give you an example. Actually, I want to give you several examples. So, So suppose we have a ring Z and a ring Zn of reminders modular n. Then the map taking K to the K modular n is a homomorphism of rings. So earlier we talked about Z with addition as an abelian group and Zn with addition as an abelian group, and Z to the n. So we consider this map as a map of abelian groups. But now, if we add multiplication into the game, so Z becomes a ring, Zn becomes a ring, and this map becomes a ring homomorphism. So this is exactly the same map. So these are exactly the same sets as before when we dealt with abelian groups. But now the only difference here that we assume that Z has two operations, the multiplication and addition, and Zn also has two operations, the multiplication and addition. And the fact that this map preserves both operations means that this is a ring homomorphism and not just a homomorphism of groups. So that's the difference between what we did before. Also, example number 2, let's say R is the field of real numbers with usual addition and multiplication, and M and R is the ring of all square matrices. Then we have a map taking any element lambda from R to the scalar matrix lambda times E, where E is the identity matrix. Then this map is a ring homomorphism. So this is a ring homomorphism. What are other examples I want to present? Okay, a third example. Suppose that we have the ring of polynomials with real coefficients. Then, and C is the field of complex numbers. Then we can take arbitrary polynomial to its value at the element I, where I square is equal to -1, imaginary unit. So this substitution becomes a ring homomorphism. So this is a ring homomorphism. Okay, now another example. Let me formulate the next example as a claim. So claim. This is another retake on the Chinese reminder theorem. So if we are given two integers m and n, and they are coprime, then we have this map from zmn to the direct product of zm times zn. And here we have addition and multiplication. And also here we have addition and multiplication coordinate-wise operations. And the map was given by taking K to K modular M and then K modular N. So the claim says that this map is an isomorphism of rings. So let's say the name of the map is phi. So phi is an isomorphism of rings. Well, we already know that this map is a bijection and it preserves the addition. And actually, when we proved the version of this result with the star here, we checked that the map phi preserves the multiplication. So the only thing that we need to check now is that phi preserves the identity element, but if we take K to be 1, it goes to 1, 1, which is what we need for the third property. So I'm going to skip the proof because the proof was somehow given in different earlier when we proved the same result but for the groups. We already checked all the things. We already know that it's a bijection, it preserves all the operations. But it's important to formulate this as a claim. Okay. Well, now I have like 10 minutes and I want to give the last definition. Yeah, there are a lot of terms today, like it's like long, boring lecture where we have to study new terms. Well, you know, math is actually a language. It's closer to English than to physics, actually. Well, if you want to learn math, you have to learn a new language. So you have to learn a lot of new terms and what they mean exactly. So that's why we have to spend our time on discussing some new words, new terms, and new notions, because math is a language. It's not a science, just in case. Okay. Now, if we are given a homomorphism of rings, suppose that R plus dot is a ring, and S plus dot is another ring, and we're given a homomorphism between these rings. Then I want to define the kernel and the image of the homomorphism. So, the definition, what is the kernel? So, the kernel is the set of all elements, say, x from R, such that phi of x is equal to 0. So, all the elements go into the 0. So, to the neutral element of the addition, not multiplication, addition. And the image of phi is the set of elements phi of x, where x goes through the elements of the ring R. And the kernel is a subset in R, so here inside the source, and the image is a subset here inside S, inside the target. And what I want, okay, so what I want to discuss is what kind of properties do we have here? Like in general, the kernel is actually an ideal, and the image is always a subring. And if we want to check that a homomorphism is surjective, we need to check that the image coincides with the whole set S. And if we want to check that the map is injective, it's actually sufficient to check that the kernel consists only of the 0 element. So let me formulate this as a claim. So the claim, suppose that R and S are rings, and phi from R to S is a homomorphism. Then, problem number 1, kernel of phi is an ideal of R. So it's a subset of R, so it's an ideal of R. The second thing, the image of phi is a subring of S. The third property, the phi is injective if and only if the kernel of phi is equal to 0, which means it contains only the 0 element. And the last property, phi is surjective if and only if the image coincides with S. Well, here the Captain Obvious came to me and told me this property, as you may guess. So it's just a trivial reformulation of the definition of the image. But all the other properties are the interesting ones. Well, we have like 4 minutes. I'm not going to rush. So I just want to clarify several things. So if you remember, we have exactly the same claim, but for the groups. And in case of groups, the kernel was a normal subgroup and the image was just a subgroup. So here, as you can see, the notion of the ideal is somehow an analogy of the normal subgroup in case of a group. Okay. So what do we need to check? Let's start with the first property. So we want to check that the kernel is the ideal. But we know that this map, well, if we consider R with addition and S with addition, our map phi is a homomorphism of groups. That was the part of the definition. It must preserve the addition. So from the version for this result about groups, we know that the kernel with respect to addition is a normal subgroup of R+. So here it's a normal subgroup. Well, addition is commutative, so it doesn't matter normal or not, every subgroup is normal. But what is important here that the other version of this result explains that the kernel with addition is a subgroup. So now we have to check on the second property of the ideal. We want to show that for any element R from the ring R and any element X from the kernel of phi, R times X is in the kernel and X times R is in the kernel. This is what we need to check. But how do we check that something belongs to the kernel? We should take its image, and if it's 0, then it belongs to the kernel, and if it's not, then it's not in the kernel. So let's take an arbitrary R, arbitrary X, and let's compute phi of Rx. Then since phi preserves multiplication, it's equal to phi R, phi X, and since X was an element of the kernel, this thing is 0, so the result must be 0. Yeah, I didn't explain here. Let me clarify one thing. I didn't explain why multiplication by 0 gives a 0 element. So let me. So here we have to show that S times 0 is equal to 0. Well, this is well, it's not that important if you don't understand how to prove this. The most important thing is to know that if you multiply in a ring, if you multiply something by 0 from the left or from the right, the result also be 0. It's not a part of the axioms, but you can prove it. And here is how you can prove this. So you know that 0 plus 0 equals 0, and now you multiply this equality by s. It gives you this, and then you use the distributivity of the multiplication. You'll get this, and now you see this element plus this element equals the same element. You subtract s times 0 from both sides, so you take minus s times 0, and the result will be s times 0 equals 0. So this explains why the last equality holds. So this is just for completeness. Okay, where the time, we don't have time actually. Well, okay, let's do this. I'll spend a couple, well, I need like a couple, like 3 minutes to complete the proof. I hope it's okay, since the next lesson will be our seminar with the group 191. So I think it's okay if we spend a couple of minutes here to prove the result. So for the second part, we have to show that the image of phi in S is a subring. But again, by the applying this this result about groups, like if we have a homomorphism of groups, then the image of phi with respect to addition is a subgroup inside S. It's a subgroup. It's exactly the same result as before, but we applied to get that the image is a subgroup with respect to addition. So the only so we have to prove two things: that the image is closed under multiplication, and the identity belongs to the image. So we want to show that if x and y are in the image, then the product is in the image. That's the first thing we need to show. And the second thing, we want to show that the identity of the ring S belongs to the image. So how to prove the first claim? The first claim is, well, if x is in the image, then x is of the form phi of A. And if y is in the image, then it's in the form of phi of B. And x times y is in the form phi of A times phi of B. And since phi preserves the multiplication, it's phi of A times B, which is in the image. And the second is even easier. Well, since phi of 1 is equal to 1, this simply means that this guy is in the image. And that's it. So we have checked all the properties for being a subring. So, and the only thing what's left is to show that phi is injective if and only if the kernel of phi is equal to 0. But again, since phi is a homomorphism of the additive groups, like if you forget the multiplication, we know that in this case, phi is injective if and only if the kernel of phi is 0. The kernel of phi, when we consider phi as a homomorphism of groups, but kernel of phi, when it's considered as a homomorphism of groups, is exactly the kernel of phi when it's considered as a homomorphism of rings. So just by the result about groups, so since this is a homomorphism of groups, then phi is injective if and only if the kernel of phi is 0. So this is a well-known, so this is the result we already know. So we just derive the result about rings from the result about groups. And this completes the proof. The item number 4 is just trivial. So let me show you what we have proved. We just proved this result that if we have a homomorphism between two rings, then the kernel is an ideal. the image is a subring. Injective, to check that phi is injective, we just need to check that the kernel consists of the 0 element. And for surjectivity, we just need to compare the image and the right-hand side, which is S. Okay, if there are any questions, please ask. If there are no questions, then in 5 minutes, there will be the seminar for the group 191. Okay, since there is no questions, thank you for being here. Well, it was a little bit boring today, but I promise the next time it will be much more interesting. Thank you, guys.
Thank you.
Thank you.
Thank you. Goodbye.
Yeah, I'm not stopping the stream. The seminar will be here in 4 minutes, like in 5 minutes. Okay, hi guys, again.
Hi again.
Well, we have to deal with rings. We're gonna become the lords of the rings, so we have to understand what the rings are, what these creatures are, how to deal with them, how to solve problems, and why are they useful. That's the most important question. So, well, we will use rings for several things. The first of them, we will implement random generators using finite fields, and it's called Galois generator, Galois random generator. That's one of the options. The second thing, they are used in cryptography instead of ZP star. So that's the second thing. Well, actually, there are a lot of other options, but we don't have time to discuss this. But believe me, we will see how they used in applications. But first of all, let's start with, but by the way, should I recall the definition of the ring? Okay, but yes, okay. So before doing this, I just want to explain the philosophy here. So how do you remember the definition? So you want to have a set with a pair of operations. One operation is addition, which is good, and the second operation is multiplication, which is almost good. So that's how you should think of it. So what is a ring? A ring is a set where you can add and multiply elements, and that's it. Well, the axioms just say that the addition and multiplication satisfy some properties, but basically what you want to add and multiply elements. And if you have something where you can multiply and add the elements, then this is basically a ring. Well, it may happen that some axioms fail, but well, in this case, this is not a ring. But in general, in many examples, all the axioms are easy to check and they hold. So let me repeat the definition. So what is a ring? So you have a set. You have an operation called plus, and this is addition. And you have another operation which is called multiplication and is denoted by the dot. And this is multiplication. And then you want the axioms. The axiom number one R with the plus. So if you consider the set R with just the first operation, which is addition, is an abelian group. I'm sorry, is an abelian group. And let me state this explicitly. So explicitly, this simply means that 1A plus is associative. One B, there is neutral element. A plus 0 equals 0 plus A equals A. 1C, there is inverse for each element A, there is an inverse element. For any A, there is element minus A, such that A plus minus A equals minus A plus A equals 0. So this is the inverse element with respect to addition. And 1D, the addition is commutative. So A plus B equals B plus A. So this is what the first property means, that the addition must be associative. By the way, should I clarify what it means? is there anyone who doesn't understand what it means precisely that the addition is associative? Should I clarify it to anyone? Okay. But basically it means that we don't care about the brackets. The order of the operation doesn't matter. So that then we need the second property, which means that so now, but until now, we have conditions only on one operation. Now we want to pose a condition which explains how the addition and multiplication are related to each other. And this relation is distributivity law. We want A times B plus C equals A times B plus A times C, and also A plus B times C equals A times C plus B times C. This is distributivity. This is the second property. The third property, we want multiplication to be associative. We don't want to deal with brackets. We don't like brackets. And the fourth property, we want to have the identity element. There must be one such that 1 times A equals A times 1 equals A for any element. So this is the definition of a ring. So this is the complete list of axioms. So 4 axioms for addition, 1 axiom for the relation between addition and multiplication, and 2 axioms for the property of multiplication. So it's not a group with respect to multiplication, just in case. So R with multiplication is associative and has neutral element, but the elements are not necessarily invertible with respect to the multiplication. That's a crucial difference. So multiplication is just an operation which is associative and has the neutral element. And then we can add property number 5. I want to maximize this. So the property number 5 says that AB equals BA, which means that the ring is commutative. And then there is other pair of properties. The property number 6 says that every element A, which is not equal to 0, where 0 is the neutral element for the addition, there is element A inverse such that A times A inverse equals A inverse times A equals 1. And the property number 7 says that 1 is not equal to 0. So just in case, when we go from 1 to 4, I mean, this means that we were given a ring. When we go from 1 to 5, which is here, it means that we're given a commutative ring. And when we go up to the property number 7, this means that we're given a field. And even in case of the field, R with multiplication is not a group because not every element is invertible. 0 is not invertible. All elements except 0 are invertible, but the 0 element is not invertible. And it's actually impossible to produce a ring where 0 element is invertible. Well, except in case of the trivial ring consisting of 1 element, the example I gave after the definition. So this is the definition of a ring. Are there any questions regarding this? Okay, so we discussed several properties of the elements of the ring. So let's check several examples. So I will remind the definitions while we compute something. So let's consider like Z12. Okay. So, and there are 4 different types of elements. First of all, invertible elements. Then we have 0 divisors. Then we have nilpotents. and then we have nilpotents or idempotents. So, well, the invertible element is an element such that xy equals yx equals 0, x equals 1. Zero divisors is an element x such that xy equals 0 and y is not 0. Nilpotent means x to the n equals 0, and idempotent means x to square equals x. So this is just a brief reminder of what these properties mean. So let's try to describe all the invertible elements, zero divisors, nilpotent elements, idempotents here. But how do you think? Well, I mean, in case of the ring Z, do you remember the answer in case of the ring Z? What are the invertible elements in the ring Z plus and multiplication?
It's like 1.
Not just 1, plus minus 1.
But
How do
we
you
have
know?
Z12. Isn't that from we have Z plus. I thought
Yeah.
answer for Z12. Isn't
Let's take
What?
the integers. Let's switch to a simpler example, which was given on the lecture.
okay.
Z plus and addition and multiplication. Then the invertibles here are just plus 1 and minus 1. Okay? So the zero divisor is only 0. Is it clear why?
Yes. Yes.
Okay, are there any questions regarding this, just in case? Okay, so the only nilpotent element is also 0. And there are only two idempotent elements, 0 and 1. So as you can see, well, it's not a lot. Like there are infinitely many elements and only finitely many elements goes inside this classification. So let's see what happens here. But first of all, what is your intuition? How do you think? Well, the answer for the first item we already know. But what is your intuition about other cases? Do we have anything new in comparison to this case? How do you think?
Yes.
Yeah.
Okay. Okay. So let's discuss the invertible elements again. So we know that the invertible elements are just all elements co-prime with 12. So we know how they look like. So, but let me do this. I just want to write all the elements of the group of the ring Z12. So these are all the elements. So let me let me underline all the invertible elements. What are the invertible elements? All the elements co-prime with 12. So this is 1, this is 5, this is 7, and this is 11. So these are the invertible elements of Z12. Okay. What are the zero divisors?
0.
Okay.
2, 3,
2, maybe the rest.
4.
Yeah, the
0,
rest.
2, 3, 4, 6, 8, 9, 10.
So let's see why, for example. You see, if you multiply 2 by 6, you will get 12, which is 0. If you multiply 3 by 4, you will get 12, which is 0. So if you multiply, say, let's say 9, yeah? If you multiply 9 by 4, you will get 36, which is divisible by 12, which is 0. So if you are not co-prime, for example, like here, well, let's say 12 is equal to 2 times 2 times 3, yep? If you are not co-prime with 12, for example, your number is equal to 3 times something. Then you take this product, which is 4, and this product is not 0 because it's not divisible by 12 because we excluded 3 here. So this element y is not 0. But if you, and let me choose a different notation, let's say a here, 3a, and this is your x. And then x times y is equal to 0 because it's divisible by 12. This is why all the elements which are not coprime are 0 divisors, because you can skip one multiple here. The product of all other primes is non-zero element of Z12, and as the result you will get a 0 element of Z12.
Sorry. This result is obviously generalizable to any Z ring, yep?
Yeah,
But
it's to any Zn.
Yeah. But can you generalize it to like any kind of cyclic rings?
But what does it mean that you have a cyclic ring? You mean Zn?
Can you say that a ring is cyclic if it is generated by one generator?
But what does it mean exactly that it's generated by one element? I mean, here we have two operations. So you will add and multiply this element by itself many times. I mean, it's an interesting question how to define the notion of a finitely generated ring, or like what is an analogy of a cyclic group here. Well, this gives you the notion of a polynomial ring, of a ring of polynomials in one variable. And we will discuss polynomials in one variable the next time. And yes, you can generalize this to the case of polynomials. But okay, but then you will have, well, then it's just impossible, I would say. It's almost impossible. Okay, Andrei is saying that what if we define a generator to be a multiplicative generator? But there are almost no rings with this property. I mean, even Zn doesn't satisfy this property. So yeah, it's very important to give a definition in such a way that the set of examples is not empty. If the definition provides you with an empty set of examples, that's really bad. It's not interesting definition. Okay, so we covered two cases, the invertible elements and the 0 divisors, but more or less we already knew the answers here. So let's try to compute the nilpotent elements and the idempotent elements. Well, how do you do that? Well, it's simple how to compute this. Yep. You just check every element, rise it to the second power, and compare result with the element itself. And if the result is the same modulo 12, then it's an idempotent. If the result is different, then it's not an idempotent. So you just have to rise to the power of 2 every element here, and you're done. But that's not very funny. But technically, this is how you solve this problem. So if you don't remember any tricks, if you don't know any methods, you just go through all the elements, and you just compute the left-hand side, the right-hand side, and you will get the answer. But in any case, the element 0 will always be an idempotent. The element 1 will always be an idempotent. So how do you think? How many idempotents are here? What are other options?
I suppose there are 4 idempotents here.
Yep,
Like
and actually 9.
Or 9. Well, you ask the number of them. Yeah.
Ah, okay, that's what you meant. So there are only 4 idempotents, 0, 1, 4, and 9. So the simple way to find them is just to compute. But let me explain how to find them in a more intelligent manner. how to search for them. So Z12, we know that it's isomorphic to Z4 times Z3, and this is an isomorphism of rings. So if you take an element A, it goes to an element A modular 4, A modular 3, okay? So this is how this isomorphism works. But now, since this is isomorphism, it means that if an element is an idempotent here, then it stays an idempotent after our isomorphism, and vice versa. If an element here was an idempotent, then the corresponding element here is an idempotent, because this is an isomorphism. So instead of searching for idempotents here, we could search all possible idempotents here and then map them through the inverse map, and this will give us the result. So is it clear what's going on now? Do you have any questions regarding this plan?
No.
Okay, so now our plan is to find all possible pairs such that this pair squared equals this thing. But how does squaring work here? I mean, how do we multiply one pair by another pair? We just multiply it coordinate-wise. So by definition, it's just a squared, comma b squared. That's just the definition, how the multiplication here works. So, and this simply means that we want to find all possible pairs A, B such that A squared equals A and B squared equals B. So we just reduce the problem of searching for the idempotents here to the problem of searching of all possible pairs of idempotents here and here. But since Z3 and Z4 are smaller, it's really, it's much easier to find idempotents there. So it's clear that, for example, in Z3, there are only two idempotents, 0 and 1. And also it's clear that there are only two idempotents in Z4, which is 0 and 1. So all possible idempotents here are 0, 0, 1, 0, 0, 1, and 1, 1. So here we use just brute force because it's simple. And now we just need to find the elements corresponding to these ones. And how do we do that? Well, on the previous seminar, we discussed the method. So we just need to find the greatest common divisor of 4 and 3, represented as a sum with some coefficients. So in this case, it's just 1 equals 4 minus 3. So in this case, the minus 3 is an element which is 1 modular 4 and 0 modular 3. And the element 4 is the one which gives you 0 modular 4 and 1 modular 3. And then 1 comma 1 is just the sum of these two guys. And or in other ways, since this guy is the identity element of this one, and the identity element is preserved by the by any isomorphism, and actually homomorphism, then it must correspond to the element 1. And also, if you want to represent it in the normal form from 0 to 11, then you just replace it by 12 minus 3, which is 9. So this gives you the list of all possible idempotents here. So, are there any questions regarding the method I presented here?
No.
Okay, now I just want to give you an important remark. So if you consider the ring Zp to the n, where p is prime number, then you may, well, it's possible to prove that for this ring, there are only two idempotents, 0 and 1. So in general, you don't have to apply the brute force for this particular case. So this is our case. So here is z2 to the 2, and here z3 to the 1. So in these rings, you will always have only two idempotents, 0 and 1. And this is your secret weapon, actually. So this is how you use the Chinese remainder theorem to compute all possible idempotents here. You just represent this ring as the product of rings of this form, where here you have powers of primes, and then you just take 0 and all possible choices for 0 and 1 in all coordinates, and this gives you the list of all possible idempotents, always. So 100% win rate for this algorithm. Okay, so now.
Sorry, can I ask a question?
Yep.
What if we have number, for example, 11? This trick won't be possible.
So if we take Z11, yep.
Yeah.
If we take Z11, well, in this case, there are only two idempotents. So it's a power of prime. It's already a power of prime like this one. So P is 11
right.
here. So there are only two idempotents, 1 and 0, and actually this is a field. Every non-zero element here is invertible, because every element except 0 is co-prime with 11.
So am I correct that we have a number of prime numbers multiplied by 2, it's number of nilpotent elements?
Again?
So biologically it follows that the number of nilpotent elements equal to all prime numbers that we have in this number multiplied by 2, because each prime number have two nilpotent elements, 0 and 1.
But okay, first of all, idempotent, not nilpotent. And the right formula is 2 to the number of primes. So if n is equal to p1 to the k1, etc., pr to the kr, then the number of idempotent elements is 2 to the power of r. Because for each we have r coordinates here. You see, we have two different primes, so we have 2 coordinates. And for each coordinate, we have 2 options. So 2 options for this one times 2 options for this one times 2 options for the next coordinate. Is it clear? I mean, Zn is isomorphic to Zp1k1 times etc. Zprkr. So we have r coordinates, and for each coordinate we take 1 or 0. So 1 or 0 here, 1 or 0 here, etc. 1 or 0 here. So how many tuples do we have here? 2 to the power of r. Are there any other questions?
No.
Okay, so let's compute nilpotent elements. So we take Z12. By the way, let's go back. I just want you to see the whole list. So now let's try to compute nilpotent elements. So all the elements such that after rising to a positive power, we will get 0. Well, first of all, a nilpotent element must be 0 divisor. So every nilpotent, so we have to check only elements with the red line here. The second thing,
I suppose prime factorization will be very handy here.
Yeah, we also will use the same Chinese remainder theorem, and it will help us to compute this. But if you want to use the brute force, I just want to explain how to do it directly. So you just consider all possible 0 divisors. And if you already computed the idempotents, so the only element which is idempotent and nilpotent, so I mean, you have both these properties, is the 0 element. So this element will always be nilpotent, but then you just skip all the blue elements here and all the yellow elements here, and you have to check only 2, 3, 6, 8, and 10 for being nilpotent.
And what are the yellow elements?
What again?
What are the yellow elements?
Here on the picture, they are idempotents.
Oh, okay, thanks.
Yeah. So and the answer will be this. I don't have a different color. Yep. There was a question.
And just 6, am I right?
6 and could you repeat?
Oh, and 0. Well, nilpotents, just
Yeah.
0 and 6.
6 and 0. That's a new color. You see, they're the only option I have here. So yeah, here are two nilpotent elements. If you raise 0 to the first power, it's 0. If you raise 6 to the second power, it's 36. It's divisible by 12, so it's 0. And these are the only nilpotents here. So let me show you how to compute this using the Chinese remainder theorem. So I will go here and I will rewrite the isomorphism again. So we have this times 3. So if we have an element A here, it goes to A times A. And if we want A to be 0 on the, let me say like this. So if an element A is nilpotent here, it's so then this pair is nilpotent here. So we're searching all possible pairs A, B, such that A to the n equals 0 in Z4 and B to the n equals 0 in Z3. So we want to find all possible nilpotents here, all possible nilpotents here, then form a pair of nilpotents and find all the corresponding elements here. What are the nilpotents here in Z3? By the way, is it clear what I'm doing now? Are there any questions regarding what's going on?
No questions? And Z3 just 0.
Is it the easy way to find all nilpotent and idempotent elements in some group?
Okay.
Just 0 in Z3.
Okay, in Z3, only 0. That's a nilpotent element. What about Z4?
0 and 2.
0 and 2. What are the possible pairs?
0,
0 and 0, 2 and 0. So that's all nilpotent. So this corresponds to 0 and this corresponds to 6. So this is how to find all possible nilpotent elements using this Chinese remainder theorem. So actually this theorem serves you a lot. Like it helps you to solve many problems. Just apply it and you'll see how fruitful this result. Are there any questions regarding this computation? Okay, so let me go to another problem.
So the union of these smaller groups is the set of all nilpotent elements of the greater group.
Which groups?
So the union of nilpotent elements of Z4 and Z3 is the set of all nilpotent elements of Z12.
Oh, well, actually not the union, but the product. You consider all possible pairs.
Ah, okay. So it's 0, 2.
Yeah. So you put all possible options for the nilpotent at the first coordinate. So it's either 0, 2, and all possible options here. So here is the only one option. You have only one option, just 0 elements. So that's why you have just 0, 0 to 0. So because it's
Okay.
you see it's a set of pairs. So you have to consider all possible pairs. So like in the case of idempotent.
Y to 0 is 6.
Y to 0 is 6 because you see you have to find an element here corresponding which goes to element 2 here and goes to element 0, 0 here. Well, the element 6 modular 4 gives you 2 and 6 modular 3 gives you 0 because it's divisible by 3.
Yeah, okay.
And also, since we know that the element 1, 0 corresponds to 9, then 2, 0 corresponds to 2 times 9. 2 times 9, well, if you compute it, will be 6 modular 12. Okay?
Yeah, okay, thanks.
Yeah, and by the way, if you do some computation, for example, here, it's easier to multiply 2 by -3, and you will get -6, and then it's obvious that -6 is equal to 6. So it's less convenient to use 9 in computation, because when you multiply 2 by 9, well, you will get a larger number. So now here 2 is not a big deal, multiplying by 2. But if you say need to multiply 9 by something larger, it's easier to multiply -3 by something larger. So don't hesitate to switch from the usual representation for a reminder to a different representation using negative numbers. It's sometimes more convenient in computation. Okay, are there any other questions? And just in case, here is the final list. So that's how we computed everything. Okay. Yeah, and by the way, also you could compute the invertible elements and the zero divide invertible elements in the same manner. So for example, an element A is invertible if and only if both coordinates here are invertible. So you may find all invertible elements for the first coordinate, all invertible elements for the second coordinate, and then all possible products give you invertible elements here. For example, in Z3, there are 2 invertible elements, 1 and -1, which is 2. And here you also have only 2 invertible elements, 1 and 3, which is -1. So 2 elements here, 2 elements here. So there are 4 options. So there are only 4 invertible elements here. But probably that's less convenient than just find all the numbers co-prime with 12. So for invertible elements, it's just easier to cross out all numbers with a common factor with 12. Okay, if there are no questions, let me go to a different problem. So let's try to deal with some general ring. Like suppose we're given a ring R with addition denoted by plus and multiplication denoted by dot, and suppose that it's a commutative ring. So suppose we're given an element x, which is nilpotent, so such that x to the n equals 1. Let's try to show that then the element 1 plus x, let's say 1 minus x for convenience. 1 minus x is invertible. Oops, it's x, it's 0. I said it's nilpotent, but I wrote 1. That was a mistake. So suppose so that's all we're given. We know absolutely nothing, but the ring is a commutative ring, and we're given an element x which is nilpotent. In this general case, it's possible to show that 1 minus x is invertible. And we can actually write the formula for its inverse. Can you guess how could we do that?
What is 1 minus x?
Okay, 1 is the identity element of the ring R. X is an element of the ring R. Minus x is the inverse element with respect to addition. So 1 minus x means that 1 plus minus x.
Okay.
So, well, it's the usual thing, like 1 plus minus x.
Yeah, I understand. Okay.
That's how you do it. Okay, yeah, but you see, for me, it's. I'm so get used to this. So it's hard to remember that I have to explain this notation. Like, but yeah, it was a good question. I forgot to explain this notation because you have like only plus and multiplication, and here I use this symbol minus without any explanation. But this is what it means.
Well, I suppose if we subtract -1 from both sides of x to the power n equals 0, and then use the knowledge we know from school that x, like, that we
Exactly.
can x -1 out of brackets, pull out of brackets and get
Cool.
something.
Yep. Yep. That's exactly how it works. Let me show you. Let me repeat your proof, but I'll do it in a slightly different manner. So we have this equality. Yep. And we have this equality, 1 equals 1. Let's subtract x to the n from the left-hand side of this equality. So then we have 1 minus x to the n equals 1. Yes, because x to the n is just 0. And now we can use the formula from the school, which says that here we have 1 minus x times 1 plus x plus and so on, x to the n minus 1. And now we see that this times this equals 1. So this is the inverse. So this is 1 minus x inverse. And that's it. Are there any questions?
Why is this 1 minus x inverse? Because it is.
Because it's
okay.
an element such that multiplying by the element 1 minus x, you will get 1, just by definition.
Okay. Okay.
So the other way how to get the answer is this. So how do you compute something like this? It's a sum of all possible powers of the element q. Well, for example, when you compute this in the usual real numbers. So this is not a proof, I'm just trying to explain how to guess the answer. So you know that 1 minus q inverse is just this infinite sum. Well, if q is the number which is strictly smaller than 1, I mean, the modular of q is strictly smaller than 1, then you have this formula. And q is a real number. We know this formula. But now it's called geometric series. But now, if q is an nilpotent element, then we would expect that 1 minus q, like we would expect, is equal to this sum if we know that this equality happens. And now, so this is just a guess. So it's not a proof. It's like a way of guessing. But now, since we have a formula, we can just check that when we multiply this expression by 1 minus q, the result will be invertible. No, the result will be 1. That's just a way of thinking how to guess the result. Okay, let's try to do another thing. So the second thing, suppose that x, again, is a nilpotent, and A in R is invertible. Let's try to show that A plus x is invertible. So the previous case was, so this is the generalization of the previous case. The previous one was when A is 1. Now we want to generalize this to the case when this guy is an arbitrary invertible. How do you think? How to show that A plus x is invertible? And how to write the formula for the inverse element?
In a similar manner, maybe?
Yeah, but how? But okay, should I do it right now, or do you want to think a little bit?
Maybe think a little bit.
Okay, I'll give you the time.
Do we have something like 1 divided by a?
You kind of put a out of brackets,
Yep.
and then there will be like
Oh, I'm sorry. That's inverse is wrong. Just this. And now we want to compute the inverse to this thing. We want to compute the inverse to this thing. But since how do you compute the inverse of the product? And here multiplication is commutative. The ring R is commutative. So this will be A inverse times this inverse. Okay? So we know that A is invertible, so this exists. But why this is invertible and how to compute the formula for its inverse? Well, if X is nilpotent, then A minus 1X is also nilpotent because this power, because of the commutativity, means that we have this and the result is 0. So this is also a nilpotent element. And then its inverse is 1 minus X plus A minus A inverse X squared, etc. So by the previous formula. So the result will be A plus X inverse is A inverse, and here 1 minus A inverse X plus A inverse X squared, and so on, plus minus A inverse X to the n minus 1 bracket. So this is the inverse element. Are there any questions? Should I repeat something? Should I explain what's going on here? Yeah, by the way, Andrei, you're right. That's exactly what I used here, that if you multiply an nilpotent element in a commutative ring by anything, the result is a nilpotent element. So this is how we use it. But what you must remember here, if you take an invertible element and add a nilpotent element, the result is always invertible if the ring is commutative. Let me show you the next problem related to this property. Let's consider the ring Z9X, the polynomials with coefficients in Z9. So just in case, what are the polynomials? Polynomials are these pictures. So two polynomials are the same if and only if their coefficients are the same. So the polynomials are not functions, but you still can multiply the polynomials by the usual rules, like what is this? Like if you want to compute something like this, you just use the usual rules. 2 by 1 is equal to 2, plus 2 by 4 is 8x squared, plus 3x, plus 3 by 4 is 12x cubed, and everything is done in Z9. Now you can reduce the result modular 9, so it will be 2 plus 8x squared plus 3x plus here 12 modular 9 is 3, so it's 3x cubed. So this is how to make computations with polynomials. So when you want to multiply, you just apply the usual rules. So are there any questions?
What does it mean, ZGX?
Oh, it's not G. I'm sorry. For my handwriting, it's just awful. It was Z9.
Ah, Z9.
It's not, yeah. I'm sorry. It was awfully written. It just Z9, just the ring of reminders modular 9. So the numbers from 0 to 8. And now this is
of Z9?
Yep.
Okay.
It's not a field. It's just a commutative ring.
I see, yeah, okay.
So all these coefficients are the elements from Z9, and the X is just a letter. So it means nothing to multiply an element of Z9 by some symbol X. So that's why it's just a picture. So polynomial is just this picture. An operation of multiplication like here, and addition, they are just ways of rewriting pictures. Well, everything in algebra actually is formal. Everything in algebra is just writing pictures. So if I want to add, for example, these two polynomials, 2 plus 3x plus 1 plus 4x squared. So if I want to add them, I simply add them in the usual way, 3 plus 3x plus 4x squared. So the rules are exactly the same, but the rules work with pictures. So these are not functions. So if you want to compare two polynomials, you just compare them coefficient-wise. You don't substitute anything inside x. You just see that the coefficients are distinct. Well, there is at least one different coefficient. These are two different polynomials. No, you don't need to substitute anything. So that's the beauty of being a polynomial in algebra. In analysis, if you want to compare two polynomials, you have to substitute a number at each number at instead of x and compare the result. So this gives you this transcendental procedure of comparing, which is awful, but here it's just comparing of coefficients. Okay, are there any questions regarding the operations here?
Could you explain one more time the way of comparing polynomials?
Okay, so it's simple. So for example, if you have x and you have x squared, they are different because here coefficients near x to the power of 1 is 1, and here the coefficient near x to the power of 1 is 0. You see, these are two different coefficients. That's why the polynomials are different. So you just compare them coefficient-wise.
The
so
coefficient before the powers.
What again?
The coefficients near the powers.
The coefficients near the respective powers of x. So you have the first power of x here, and you have the 0 power of x here. So you need to compare these two guys, check, and you want to compare these two guys. And if both of them are the same, then these are the same polynomials. And if at least of them is different, like for example, a0 is not the same as b0, then the polynomials are different. Or if you have like something here, and there is no x squared here, then they are different automatically. So just use coefficients to compare polynomials. Is it clear? But so I mean, are there any questions regarding the comparison of polynomials?
Yeah, thanks.
Okay, so now, so let me repeat, we're trying to deal with polynomials here. Let's consider a polynomial like this, 2 plus 3x squared. How do you think? Is it invertible or not? So this is as an element of this ring. Is it invertible or not?
No.
Are there any other? Is there anyone who thinks that this polynomial is invertible? No one. Let's check that it's invertible. It's actually invertible. So we may find a polynomial such that multiplying by this new polynomial, the product will be 1. By the way, the identity element here is the polynomial just 1, like the usual one from Z9. But let me explain why this is invertible. You see, it's a sum of two elements. But let me use different colors. The element 2 is the element of Z9. It's invertible. Yep.
Well, maybe we should like multiply it by something that will turn it into a constant, and then multiply by something will turn constant to 1.
No, it's not that easy. It's more complicated, but let me show you how to do that. You see, 2 is invertible in Z9. So 5 times 2 equals 1 in Z9.
And 3 is nilpotent, so
Yeah, 3 is nilpotent, exactly. And 3 to the power of 2 is equal to 0 in Z9. In particular, 3x squared to the power of 2 is 0 in Z9x. Because how do you rise to the power? Well, you just multiply the coefficients and you add powers. So because this is 3x squared times 3x squared, and the result is 9 times x4, which is 0. You see? So this is a sum of an invertible element with a nilpotent element. So it's invertible. 1 plus...
I'm not quite sure about my calculations. I just tried like 2 minus 3x squared and then multiplied by 5.
well, no, the result is wrong because the free term must be 5, not 1.
Yep, I see.
But let me show you how to compute the inverse. So we have 2 plus 3x squared. Let's put 2 outside of the brackets. So we will get 1 plus, and here we should write 2 inverse, which is 5 times 3 x squared. Okay. Oh, you probably wrote, okay, you probably forgot to multiply by 5 the result. We will see if you are right or not. So now, this is 2 times 1 plus 5 times 3 is 15. 15 modulo 9 is 6. Okay? And now we want to find the inverse for these elements. So we're looking for the inverse. So this will be the product of inverse elements. So the inverse for the element 2 is 5. And the inverse for this element is what? 1 minus 6x squared plus 6x squared to the power of 2 plus and so on. But already this power is 0, so all other powers are equal to 0. So the inverse is just 5 times 1 minus 6 to the power of 2. And 6 minus 6 modular 9 is just 3. So you can write it like 5 times 1 plus 3 x squared. And then you just open the brackets and you get 5 plus 15. And 15 is 6 modular 9. And this is the inverse element. So if you take this polynomial and multiply it by this one, you will get exactly the identity. Just in case, should I repeat the computation or any explanation here?
Could you repeat the rule, please? So sum of any element with a nilpotent element is invertible.
Sum of invertible with a nilpotent is invertible.
Okay.
So let me write it here. So this guy is invertible, and this guy is nilpotent. So you see, there is this weird ring where you have a polynomial of a positive degree, but it's still invertible. So it may happen. Well, I think it's pretty fine that you have such result. But I believe it's clear how I expanded this expression here. And if you don't understand why all these powers are 0, please ask. I will explain. But the result here is just these two first summands. Okay, are there any questions left regarding this problem? Cool. Okay, I want to cover the last topic for today, which is the notion of homomorphism. So let me just recall the definition. So if we have a ring R and a ring S, so these are rings, then homomorphism is a map from one ring to another ring, and it must preserve all the operations and the identity element. So it must preserve the addition, it must preserve multiplication, and it must preserve the identity element. So in case of abelian groups, in case of groups, we just need to preserve one operation and automatically preserve the neutral element. But this happens because the operation was really good. In case of rings, only addition is a good operation. So if we preserve addition, then we also preserve the zero element. But multiplication is not necessarily a good operation. So we need not to preserve identity in general if the second property holds. So we have to pose this additional assumption that one goes to one under our homomorphism. So don't forget this when you give the definition of a ring homomorphism. So this is the definition of the ring homomorphism. So let's try to compute some, well, let's try to describe some homomorphism. Like, let's say we take the ring Z, the ring of integers, and let's take an arbitrary ring R. So this is just an arbitrary, absolutely arbitrary ring. Let's try to describe all possible homomorphisms from the ring Z to an arbitrary ring R. But before we do that, just in case, are there any questions regarding the definition?
It should probably be phi of A times phi of B, not phi of AB.
All right, you're right. That's, you know, it's the problem when you think about things and you write different things. You still see the things in your mind, but not what's written on the paper. Yeah, thank you very much. That was a mistake. So how do you, well, so let's take an arbitrary, so let's take the element 1 from the ring. So first of all, if we take the element 0, it must go to the element 0 for any ring, because we know that homomorphism preserves addition, and so that's it's preserved the neutral element with respect to addition, which is 0. Also, by the definition of a homomorphism, we know that the element 1 must go to the element 1. Okay? Where 1 here denotes the neutral element of the ring R. Also, since phi is a homomorphism of the additive groups, so if you remember, we proved that every homomorphism of groups takes the neutral element to the neutral element and takes the inverse element to the inverse element of the image. So here it means that phi of minus A equals minus phi of A, because here we use the additive notation for the operation plus. So that was the part of the claim about homomorphism of groups. So it means that minus 1 goes to minus 1. And now the element 2, for example, equals 1 plus 1, and it must go to 1 plus 1, which is 2 here. Well, we will just denote it like, well, the sum of two identity elements of the ring R, we will denote also by 2. So as the, well, you may, so as you may see, there is only one map from the ring Z to any other ring. And this ring works as this. You take integer n, and it goes to n times 1, where 1 is the identity element of the ring R. So this is the only homomorphism from the ring Z to any other ring. There are no other homomorphisms. Was it clear?
Yep.
Okay. So, for example, when you consider a homomorphism from Z to Z, you may consider two different types of homomorphism. A homomorphism of groups or a homomorphism of rings. As a homomorphism of rings, there is only one option for when you take n to n, the only identity mapping, because it's given by this rule. But there are many homomorphisms of groups. As you remember, you can map the element 1 to any element of the group on the right. So the homomorphism of groups are of this form. N goes to n times k. So there are infinitely many homomorphisms of groups. So just in case, there are many homomorphisms of groups from Z to Z, but only one homomorphism of rings from Z to Z. Because in the second case, we also want the map to preserve the multiplication. Okay, now let me discuss another thing. So suppose, well, we're giving like, yeah.
What if we like switch spaces multiplication addition and call it? Oh no, it won't work. Yeah, no, it won't work.
It won't work because, yeah, with respect to multiplication, you cannot switch multiplication addition because Z with multiplication is not an abelian group. It's not a group. So it's impossible.
Yeah.
And actually, it's impossible in general because the zero element is never invertible with respect to multiplication. The only case when it's invertible, actually, is when your ring consists of one element only. So
Zero.
If we switch, then most probably 0 will be mapped to 1, not to 0.
Again?
I mean, if in my idea, if we try to switch these two operations, then 0 would be mapped to 1.
Yeah, of course, the neutral element here is 1, but
well, in Z, I guess in Z, I get it. In Z, it is not a group. Yes, I see.
Yeah, this element doesn't exist because you want this thing to be an abelian group with respect to multiplication, but the element which denotes 0 must be invertible with respect to multiplication. But it doesn't exist. This element doesn't exist.
And if it was a field, would it somehow work or not? Really?
No, even in case of the field, it doesn't work because there is no inverse for 0. If you take Q, the rational numbers, this is also not an abelian group. Is not a group because for the group, what you want, well, first of all, you want it to be associative, which is checked. You want it to have the neutral element. Yes, it has the identity. And now you want every element of Q to have inverse element, like there must be B such that AB equals BA equals 1. But if you take A to be 0, it means that you're seeking for the element B such that 0 times B equals B times 0 equals 1. But that's impossible because the left-hand side is 0.
Yep, I see. Yeah.
So it never works. So this makes it clear. So that's why you don't have to specify which operation is addition and which one is multiplication, because there is only one operation satisfying the required property. Like only one of them could be addition. And by the way, as I see well, we have like -1 minute left, but I still want to cover one example. So if you don't mind, we just proceed and take it. It takes like 5 minutes. Okay.
Excuse me. And is
Yep.
Z plus? No. Ring must have two operations.
Yes, you always must have two operations. Z
So
with
Z
addition.
plus and multiplication is a ring.
Yeah, this is a ring.
Okay.
This is just a Abelian group.
Yeah. Okay. Thanks.
And if you take this, well, it's not a group. Well, it's called actually monoid. It's weaker than a group. It doesn't matter. You may forget the term just immediately after you see it. But what I mean that if you skip at least, well, all three options gives you different algebraic structures. Okay. Are there any other questions? Okay. So what I want to explain now is this. So suppose that you have a ring A. A is a commutative ring. And suppose that B is another ring containing A as a subring. So this is also a ring. B is not needed to be commutative, but it doesn't matter. If you wish, you may think that B is commutative. So A is a subring of the ring B. Now I want to describe homomorphism of polynomial rings over A to the ring B. So what are the elements here? Here elements are just polynomials. So if you take a polynomial here, it's just a sum of the form ak x to the k, where k goes from 0 to some natural number n. And I want to map it to something. So what I'm saying that every map has the following form. I take an arbitrary element B from the ring B here. Oh, by the way, I want to describe all possible homomorphisms such that for any element A of the ring A, so for any element from the subring, we take this element to itself. So we act trivially on this subring. So we want to map all elements of all coefficients to exactly to this subring by the identity map. So if you want to describe all the homomorphisms with these restrictions, then they are of this form. You take an arbitrary B here and you map F to F of B, which means that it goes to the element of this form. So a homomorphism which acts trivially on coefficients is just a substitution. So this is what I want you to know. So if you want to consider a homomorphism from a polynomial ring to any other ring, then it always be a substitution. For example, if I want to produce a homomorphism from the ring R of X, for example, to the field C, the only option I have, I take a I should fix some complex number. For example, I may take 2 plus I from C. Then it defines me a homomorphism like this. And this will be a homomorphism denoted by this element. If I take other element like 1 plus 3i from C, then it gives me a different homomorphism. I denote it by phi I plus 3i, which takes f to f of 1 plus 3i. So this is how homomorphism of polynomial rings work. So I take the coefficients of R exactly to the same real numbers, and x goes to element 2 plus I. And in the second case, it goes to 1 plus 3i. We will discuss these homomorphisms in details later on the next seminar and during the next lecture, but I just want you to know the result. So I want you to be familiar with the result, because you know many things in math, they require you to get used to them. You need some time to pass in order to feel free with them. But just in case, do you have any questions regarding the claim I formulated here? Okay.
Can I ask you some questions later?
What again?
Can I ask you some questions later?
Oh, if you wish, okay. If you have questions, we may stop the seminar, and then I can start the consultation via my private Zoom account. If you want it to happen just right now, we can do it right now.
No, not right now, but later.
No problem. You may write me an email. You may write to Telegram. Just tell me if you don't have my Telegram.
Could you type it into the
Oh,
chat?
okay. Just one second. As usual, you know, it's hard to remember. That's how you identify that you're already old. It's when you don't remember your Telegram username. By the way, come on. Okay, and here it is. It's simple. It's actually simpler than I thought. Okay, guys, there are like 2 minutes before the next pair. Well, I doubt that there will be like a seminar or any other lesson in 2 minutes, but well, it's better to over our seminar just right now. So if you have any questions, just one question more, and we will stop. Okay, so yeah, if you have any questions, just feel free to write me an email, just write to the Telegram. There is no problem. So thank you for being here. I hope it was interesting.
Yeah, thank you very much.
Thank you very much. Goodbye.
Goodbye.